The only difference is the chain rules allow me to pick up n minus 2 instead. Okay? So on and so forth. Right? So right now I'm still staying closed loop. Right? I still have the head. Okay? Now, and I keep on doing that until the end, the last guy, and I have this set of equation. This set of equation, when I try to write it, okay, so the expectation of x, okay, so let's take a look at one equation. Okay, take a look at the first equation. This equation, when you set it equal to 0, you distribute the expectation in, you will have two parts. The first part is the expectation of xn times xn minus 1. The second part is the expectations of xn minus 1 multiplied by that ugly prediction. Okay? So there are two parts. Okay? And if you separate the two parts, you have something like this. So for the first equation, I pick up expectation of xn times xn minus 1 equal to that. Okay? And for the second equation, I have this. For the third equation, I have so on and so forth, all the way to the end. Okay. Now this looks kind of messy. But we can always write it as a matrix multiplication. Okay? So how do we do this? So this is a linear combination, which is perfect for writing things as a matrix, right? So I'm going to have this terms and multiply by a whole bunch of a's, right? So I have a1, a2, a3, that's the vectors, and that's going to be equal to this vectors. Okay? So I'm going to try to write it as a matrix. Okay? And before I do that, you should recognize that the expectation of xn and xn minus 1 is nothing more than rxx of 1. Okay? So you can do all that, get to here, and then if you write it in matrix form, it will look something like this. Okay? It will look something like this. Now, what can we say about this matrix? What is this? It's a symmetric matrix. It's called the autocorrelation matrix. Okay, that I show you in one of the slides I have in the beginning. So this is the autocorrelation matrix. This is the correlation between you and yourself. This is the correlation between you and your next door neighbors. This is whatever with a 2 means the correlation between you and your second door down neighbor. Okay? That's all there is to it. And over here you also have the same thing. This is the correlation between you and your next door neighbor. This is the correlation between you and your second door down next door neighbor, so on and so forth. And if I write it, so this is the correlation matrix for the Y-sense stationary process. And this is called the cross correlation vector. Okay? And we can write it in a very simple matrix form, which is Rx times the vector A is equal to the vector P. Okay? And the optimal A will be given as Rx inverse times P. So this is the classic Wiener solution, okay? Discrete Wiener solution for linear prediction. Okay? Now, in practice, how do we actually use this? How do we come up with this Rxx matrix and and cross correlation vectors? We do time domain approximation. Okay, we observe a lot of data, and you approximate it from time averaging of the signal. So after you observe a lot of data, you keep on doing the summations of all the correlation. Okay, sum them up, and hopefully it converges something else. Okay, but that's roughly all that we know how to do. Okay, so this is called the optimal linear predictions. People actually use this in a lot of adaptive filtering problems, and people also even use this to predict the stock market and everything without much success. Okay. So now that we know how to predict one single sample. Okay, let's try to generalize and try to predict a vector of symbols together. Okay, and in that case, we need some the framework called linear signal representations, which and to talk a lot about. Okay. So here we have an input vector x, okay, being represented as a linear combination of the phi, or the basis function. Okay. Now, these yi is called the coefficient of the linear representation, and they are obtained by taking the inner product between the input and each of the basis functions. Okay, so basically it's just a vector multiplication like this. Now the approximation is this. Okay, doing the summations over 0 to n minus 1 of everything, and suppose that you don't quantize the y. If you don't quantize the y, you get back exactly the same x as you feed it. Okay, because when you design a basis function, you will think about perfect reconstruction, invertibility, and everything. Okay, so let's take a look at this. This is the input signal. This is the transform coefficient. This is the basis function. Typically, in a compression framework, these are the guys that will be quantized, entropy coded, transmitted over the communication channel, and get reconstructed like right here. Okay, we never send the pure sample. We send the coefficient. Okay, and the goal is maybe trying to use as few coefficient as possible. That's one goal. The second would be trying to use as for the one that we keep. Okay, we should use the minimum amount of bits to describe those y that we actually kept. Okay, so that those are the two goals for compression. So if you take a look at this problem from a matrix viewpoint, matrix vector viewpoint, it's actually pretty simple. You have x coming through an analysis transform, giving you y, coming through a quantizer, and in this case I'm lazy, so I write the q and I combine my q and my q inverse together into one box. Okay, and I also have maybe my communication channel right in the middle here as well. Okay, and then so this is my encoder. At the decoder, I have, after the communication channel, after the inverse quantizations, I come up with the y hat. I pass it through the synthesis basis functions, and I come out with the x hat, which hopefully is a very close approximation of this x. Okay? So in the 1D analysis transform, we have something like this. Okay? This is my x coming in. This is my vector y coming out. And I get all these y by doing the inner product. One basis function multiplied by this, second basis function multiplied by that, last basis function multiplied by that. Okay? So at the so that's the analysis. At the synthesis, okay, you get x by a linear combination of the basis function. So you can write it this way. These are my basis function. First basis function, second basis function, so on and so forth. Okay? Now, I have the hat here to indicate the case where I might have a different basis function on the analysis side and the synthesis side. This is called the bi-orthogonal case, right? In the nicest type of transform, we have orthogonality. And what that means is the transpose, TA transpose give you TS. In that case, you just have phi here, phi0 here, phi1 here, without the hat. But that's a subset, okay? That is the nicest case. But it doesn't mean that you there exist other basis functions that have different analysis and synthesis sides. Okay, there's nothing wrong with that. In fact, in practice, like the Weber transform that we use in practice actually has the hat too. Okay, but the DCT doesn't have the hat. The discrete cosine transform is truly orthogonal, doesn't have the hat. Okay, so there are two things. First, you need invertibility, at least, okay? Because that allows us to get back the original signal, okay? If we have TS equal to TA inverse, we're fine, okay? So we know that all the error come from Q and the communication channel, not the transform, okay? That's what we want to do. So what that means is you need this condition. The dot product between phi I and phi hat of j is delta I minus k. And that's just a fancier way of writing this invertibility equation. Okay. For unitary or orthonormal transform, okay, then the transpose is the inverse. In that case, you don't have the hat anymore. All you have to do is Pi dot product with Pj give you delta I minus j. So this Fourier transform has this property. Discrete cosine transform has this property. Discrete sine transform has this property. Some of the Weyl construction that we talk about in the Jones course has this construction, right? For example, Haar Weyl has this property. So now, one of the most fundamental observations that we have in compression with respect to transform is called norm preservation. Okay, the norm preservation property of an orthonormal transform is the properties. I think I put a question mark on your slides. Okay, but what I want to show is that the norm of y minus y hat is the same as x minus x hat. That's the norm of x minus x hat. Okay? I want to show the norm of y minus y hat is the same as x minus x hat. Okay? So let me substitute y by tx, okay? And y hat is tx hat. Okay? Factor out t, so I have this, right? And how do I get norm? Let's do inner product, right? So when I do the inner product between these two guys together, I have the inner product of t x minus x hat and t times x minus x hat with the square root. That's the definition of norm, right? Norm, L2 norm, okay? So that is equal to the dot product here can be written like this, okay? And guess what? What is this? TA transpose times T. That's identity. So they disappear. Okay? What is left? So what is that? What is left? That's the norm, the L2 norm of x minus x hat. That's the L2 norm of x minus x hat. Okay? Now, so why is this important? Any idea?